Somewhere in the vast darkness of space, there exists an object so powerful that not even light can escape its grip. We call it a black hole. A region where gravity has won completely, where the laws of physics as we know them are pushed to their absolute limit. But here's something most people don't realize. Not all black holes are the same. They come in different sizes, different origins, and even different physical properties. Today, we're going to explore the major types of black holes in the universe, from the smallest theoretical ones to the monsters lurking at the centers of galaxies. What exactly is a black hole? Before we dive into the types, let's quickly establish what a black hole actually is. Don't forget to like the video and subscribe to the channel. A black hole forms when matter is compressed into an incredibly small space, creating a gravitational field so intense that it warps space and time around it. The boundary surrounding a black hole is called the event horizon, the point of no return. Once anything crosses this boundary, whether it's a spacecraft, a star, or a beam of light, it can never come back out. At the very center lies the singularity, a point where, according to our current equations, density becomes infinite, and our understanding of physics breaks down completely. Now, black holes are typically classified in two ways: by their mass and by their physical properties, such as spin and electric charge. Let's start with mass, since that's the most commonly discussed classification. Type 1. Stellar mass black holes. The most common type of black hole in the universe is the stellar mass black hole. These form when a massive star, one at least 20 times the mass of our Sun, reaches the end of its life. When such a star runs out of nuclear fuel, it can no longer support itself against its own gravity. The core collapses violently in an event known as a supernova, and if the remaining core is massive enough, it keeps collapsing until it becomes a black hole. Stellar mass black holes typically range from about 5 to a few dozen times the mass of the Sun. Despite that enormous mass, they're surprisingly compact. A black hole 10 times the Sun's mass would have an event horizon only about 60 kilometers across. Scientists have detected these black holes primarily in two ways: by observing how they pull on companion stars in binary systems, and even more recently, through gravitational waves, ripples in spacetime produced when two stellar mass black holes collide. The Nobel Prize-winning detection by LIGO in 2015 confirmed the existence of these collisions for the first time. There are likely tens of millions of stellar mass black holes scattered throughout our galaxy alone. Type 2. Intermediate mass black holes. Between the relatively small stellar mass black holes and the giants we'll discuss next, there exists a mysterious middle category: intermediate mass black holes. These range from about 100 to several 100,000 solar masses. For decades, their existence was purely theoretical. A missing link scientists suspected must exist, but struggled to confirm. The challenge is that intermediate mass black holes don't fit neatly into our usual detection methods. They're too small to dominate the center of a galaxy the way supermassive black holes do, yet too large to form from a single collapsing star. Researchers believe they may form through the merger of multiple stellar mass black holes or through the collapse of massive star clusters. In recent years, gravitational wave detectors have picked up signals consistent with black hole mergers producing intermediate mass remnants, giving us our strongest evidence yet that these objects are real. Understanding intermediate mass black holes is crucial because many scientists believe they may be the building blocks of the next category: the supermassive giants found at the heart of nearly every large galaxy. Type 3. Supermassive black holes. Now we arrive at the true giants of the cosmos: supermassive black holes. These behemoths contain anywhere from hundreds of thousands to billions of times the mass of our Sun. Remarkably, nearly every large galaxy, including our own Milky Way, appears to host one at its very center. Our galaxy's supermassive black hole is called Sagittarius A, with a mass about 4 million times that of the Sun. In 2022, astronomers using the Event Horizon Telescope captured a direct image of it, showing a glowing ring of superheated gas swirling around its event horizon. a historic achievement that let humanity see for the first time a shadow cast by a black hole in our own galactic backyard. How do supermassive black holes get so large? Scientists still debate this. Some theories suggest they grew gradually, consuming gas, dust, and smaller black holes over billions of years. Others propose they formed directly from the collapse of massive gas clouds in the early universe, skipping the stellar stage entirely. What makes supermassive black holes especially fascinating is their influence on galactic evolution. Their gravity and the immense energy released when they consume surrounding material can regulate star formation across an entire galaxy. In some cases, when a black hole feeds voraciously, it powers a quasar, one of the most luminous objects in the entire universe, capable of outshining every star in its host galaxy combined. Type 4. Primordial black holes. Our fourth category takes us into more speculative territory: primordial black holes. Unlike the previous types, these wouldn't have formed from collapsing stars at all. Instead, the theory suggests they formed in the first fractions of a second after the Big Bang, when the universe was incredibly dense and small fluctuations in that density could have collapsed directly into black holes. Primordial black holes are theorized to span an enormous range of masses, from smaller than an asteroid to larger than a mountain, and potentially even up to stellar or supermassive scales. Why does this matter? Because primordial black holes have been proposed as a possible candidate for dark matter, the mysterious substance that makes up roughly 27% of the universe's total mass energy content, yet has never been directly observed. So far, no primordial black hole has been confirmed to exist. Scientists are actively searching for evidence through gravitational microlensing surveys and by looking for the faint radiation such black holes might emit as they slowly evaporate, a process predicted by physicist Stephen Hawking, known today as Hawking radiation. Classifying by spin and charge. Beyond mass, physicists also classify black holes based on two additional properties: rotation and electric charge. This gives us four theoretical categories, described by different mathematical solutions to Einstein's equations. A Schwarzschild black hole is the simplest type. It doesn't spin and carries no electric charge. A Kerr black hole rotates, which is believed to describe most real black holes in the universe, since virtually everything in space spins to some degree. A Reissner-Nordstrom black hole carries electric charge but doesn't rotate, largely a theoretica. Curiosity, since real black holes tend to neutralize any charge quickly. And finally, a Kerr-Newman black hole both rotates and carries charge, representing the most general and complete solution. In practice, astronomers believe nearly all black holes in nature are rotating Kerr black holes, since angular momentum is nearly universal in the cosmos. Closing, from stellar remnants scattered across our galaxy, to intermediate giants we're only beginning to confirm, to the supermassive monsters anchoring entire galaxies, and even the speculative relics of the Big Bang itself. Black holes remind us how much mystery still remains in our universe. Each type tells a different story about how matter, gravity, and time interact under the most extreme conditions imaginable. And as our telescopes and detectors continue to improve, we may soon uncover even more secrets hidden within these darkest corners of the cosmos.